Tomorrow. Many of you have already had a chance to visit with her. I think more of you are going to have a chance either later today or tomorrow. She comes to us by way of Sharif University of Technology in Tehran. She got her PhD in physics at the Ludwig Maximilian University of Munich in 2015. Among her accolades, in a relatively short career so far, she's the recipient of the Minerva Fast Track Scholarship of the Max Planck Society in 2016. She was elected as a member of Schumann Kolleg in 2017 and has been a visiting scientist at the chemistry department at Harvard University and also Oxford University. And since 2020, the last couple of years, she's been leading her own independent research group at the Max Planck Institute for the Science of Light in Erlangen. She's also a fellow of the Max Planck Center for Extreme and Quantum Photonics in Ottawa, and also the Max Planck School of Photonics. So it's very exciting. She represents a really vibrant community of quantum optics and laser science and all the things that implies. And it's just my pleasure to have her come and give us talk today.
Thank you very much. So thank you very much for the introduction. Yeah, as Tom mentioned, I'm Hanieh Fattahi, and today I'm going to present you the research which is mainly done in my research group currently in Erlangen. So the title of our research group, or the name of our group in Erlangen, is Femtosecond Fieldoscopy. And most probably you haven't heard the word fieldoscopy because it doesn't exist or didn't exist. It's a woman-made name. And so I just made it for our new technique that we have developed in our lab in the analogy with microscopy and spectroscopy.
So, Hanieh, we need to do one thing because people online can't see your screen. So we need to share the screen. Sorry.
Tom, could you turn down the lights that are right on the screen?
Yeah.
I teach in the room, so I know one or two things.
Oh, perfect.
Is that better?
Absolutely.
Yeah.
So,
Sorry, carry on.
So what is my background? In the last 15 years, before I start my research group, I've been active in the development of this new type of laser technology. At that time, ytterbium thin disk laser technology. So they were quite of a hype for quite some years. And the strength of this laser was in the fact that you could scale the energy and the average power of the laser pulses in this kind of geometry. How this is possible? In principle, you have a thin layer of the gain medium. That's why it's called disk geometry. So it's most of the time, it's about hundreds of micron, and which is mounted on a diamond substrate, and it's cooled very efficiently from the backside. So that led you to scale the energy and average power simultaneously, unlike the previous laser technology, thin disk laser, titanium sapphire lasers. So what we showed during that years, we showed that we can develop these lasers to a very good extent, and one can use these lasers to pump optical parametric amplifiers to just move the central wavelengths of the lasing to new frequencies and generate short pulses out of them, femtosecond pulses. So this combination of the OPAs, optical parametric amplifiers, and thin disk lasers, we dubbed it at that time third generation femtosecond technology. This is also the title of my thesis, and it was quite successful. And after that, we demonstrated that with such a front end, right, thin disk lasers and optical parametric amplifiers, one can generate exotic pulses, which they don't have sinusoidal shape, but you can generate this light transient and shape the electric field of light down to a sub-cycle to the shape that you like and it's interesting for your experiment. So at that time, it was important for us because of the attosecond pulse generation, which is a field-driven effect. So we wanted to have a control on the electric field of the light, but you can think also about petahertz data transfer, right? And this kind of scenarios. So we moved on and we showed that these kind of lasers can be used as a front end for mid-infrared and terahertz pulse generations. We showed that they are very nicely can be used for spectroscopy. And also we developed some new techniques for petahertz electric field sampling of laser pulses. So as you know, at the petahertz frequencies, the oscillations of the electric field of light is so fast that no electronic can catch it up, right? So we pushed the frontiers of this field detection down to visible spectral range out of the vacuum, which opened so many applications, because if you are out of the vacuum, you can immediately think about live samples, right? So, and this was the field which was dominated before by attosecond streaking and in vacuum, so we brought it on the optical table. So what we do in my current lab, so since 2020, I moved my lab from Max Planck Institute of Quantum Optics to Max Planck Institute for the Science of Light. This is 1 hour away from the previous lab. In this lab, our vision is to use these advanced laser techniques and these detection techniques that we have, field detection techniques, to address some prominent applications. So we are active, we have been active mainly on sensing in 3 different categories. The first one is the femtosecond molecular fieldoscopy, which I'm going to explain in details in this talk, and that has been one of the main parts of the research in my group in Erlangen. We have been active also to use the same tools for mid-infrared pulse generation and gas spectroscopy, especially in atmosphere. And of course, as a person who generates very strong pulses, we've been active in strong field tomography, right? To look at the behavior of the matter when very short pulses with high intensity are injected to them. But just recently, since last year, we started also another category beside the sensing, and that's unsustainable solutions. So we are developing a solar laser. I won't go through the details of this project, but maybe I just, at the end, if there was time, I just show 1-2 slides on motivation. But if you want to know more, just approach me after the talk. So we are also very excited about this topic. So what is the whole motivation behind this femtosecond molecular fieldoscopy? So let's start with this very simple example. So I'm going to motivate the whole technique by biological samples, but you can use it to detect anything, right? So it doesn't have to be biological samples. So let's say that you are interested in birds watching, right? And when you are out to look at the birds, there are some WH questions that you would like to know the answer to them, right? You would like to know what type of birds are flying in front of your eyes, when the birds are arrived, where are they going, how many of them, and so on. And the only thing that you don't want to do is that your observation kills the bird, right? So you just don't want to disturb the behavior of these birds by your observation. So this is the current status of the high resolution soft matter microscopy. So we have the label, we have this kind of microscopy, which were praised by the Nobel Prize in 2014. They are advancing the frontier of biology. They are extremely powerful. You can get down to 80 nanometer spatial resolution. But the shortcoming with this kind of techniques is that you have to label a molecule that emits light to the molecules in your sample, right? And most of the time, these dye molecules are very big, right? Because you want them to emit so much light and you want to gather this light and make an image. Therefore, they perturb the function of the molecules that you would like to look at. And they are also toxic. And at the end, you don't get any chemical information from your sample. So is there any way around this? Then the answer is yes, of course. There has been several ways around this for many years. And it has a label. It's called label-free microscopy. what is the idea behind the label-free microscopy is that instead of adding a label to your sample and looking at the light which is emitted from the sample, you look at the light which is emitted or absorbed from the molecules which make your samples. So this can be at the fundamental vibrations of the bands, in chemical bands of the sample, this region, or you can look at the higher frequencies like Raman and overtone spectroscopy and microscopy. So these regions are very famous. They have a name. They are called, at this region, the matter called that it's said that the matter has a fingerprint, right? So you can really distinguish what's going on. And there are many scientists who has been working on it and pushing the frontiers of these techniques. But as the nature dictates it, so we have to excite these molecules at the mid-infrared to get to the fundamental vibrations, or at the near-infrared. And we know that, right? That by increasing the wavelength of the light, what you lose is the spatial resolution. So you get low spatial resolution images relative to the techniques that they use labeling, but there is no perturbation, or if they are not destructive, there is no toxicity, and you get chemical information. So what we are doing in my group, we are trying to turn this red cross to a green tick. So that's the motivation of the next slide that I'm going to show you. So, and this technique we called femtosecond molecular fieldoscopy. And what is it based on? It's based on a very simple idea that we are forced to excite the sample at the near infrared or mid infrared by nature. What about finding a way to send a probe at much higher frequencies to the sample and get information? Why higher frequencies? Because if you have a light at higher frequencies, you can simply focus it tighter. The diffraction limit is smaller, and that means a spatial resolution. So how to put these two together to get the chemical information and to have a high spatial resolution? Let's say that you have a cell and you would like to get a subcellular image of this component. So then you have a femtosecond pulse, which you shine to your cell. And of course, you cannot focus it so tighter than this. So that's going to be your spatial resolution. And if you look at the transmitted light from your cell, that should have the fingerprint of the cell inside, right? So if you put a spectrometer here, you are going to see absorption or emission at distinct frequencies. If you look at the things in the time domain, people, are not most of the time comfortable with the time domain picture, then you are going to see the ultra short pulse and the response of the molecules, which is lagging at the trailing edge of the pulse. So if you find a way to measure the electric field of the light and this molecular response, and you Fourier transform it, then you get exactly the same information that you get with a spectrometer. So the idea was to also just turn on a probe. So then let's have a probe at much higher frequency. And then by using the probe, you can specially gate this area. So you can get information at sub-diffraction limit of the excitation pulse. And what we do with our technique, we use the same probe pulse to read out the electric field of the light after the transmission. So this way, we spatially and temporally gate the molecular responses. What does it give us? It gives us quite high detection sensitivity. I'm going to show you some measurements because here the excitation pulses are separated from the molecular response. So you are not sensitive to the instability or noise of the laser, right? So you don't have a background if you Fourier transform only the trailing edge of the pulse. This gives you also high dynamic range of the measurement. You get high spatial resolution. And as you use femtosecond pulses, you can read the response of the molecules at once, right? Because your pulses are broadband and you can match it to the resonances that you have. So, but it all comes to the fact to find a way to read this electric field of light. And we are talking about petahertz frequencies, so there is no option except it has been the only option has been to just put it in the attosecond streaking setup. So here is the place that our detection technique comes to the play. So if you have done terahertz, or if you've been active in terahertz spectroscopy, you are familiar with the electro-optic sampling. So this has the same kind of basic with a bit of changes. So let's say that you have the red excitation pulses and you have a shorter probe pulse that you want to use and read these excitation pulses. Here I'm showing these two pulses in the frequency domain. Now what we do, we just generate a correlation signal between the excitation pulses and probe pulses, and then we read out this correlation signal afterwards. What is the correlation signal? In this correlation signal, we generate a polarization rotation, which is linearly proportional to the electric field of our excitation pulses. So what happens here is a pretty simple and I would say complicated. So here is the spectrum of the excitation pulses. Here is the probe pulses. And in this crystal, we generate the sum frequency, which is this spectrum. And if you look at these pulses, you see that they are short. So the spectrum is very broadband. Therefore, the sum frequency generation has a spectral overlap with the probe pulses. What we do, spectral overlap is good, right? Means that the phase informations are survived. So we filter this spectrally overlapped area, and then we send it to an ellipsometer and measure the polarization rotation, which is caused by this interaction point by point at the delay time. So this is somehow our magic, but of course you require the excitation pulses to be carrier to envelope phase stable. So you want the field to be identical pulse to pulse, right? Because otherwise it's going to be washed out. And if you would like to make such a system for microscopy and spectroscopic applications, so you would like to work at high repetition rate, because the biologists don't like to stand in the lab for 2 days to make one image from the sample that they have. It's also useful to go to higher repetition rate, to the megahertz repetition rate, because that's where based on this 1/f noise law, that's where the noise of the system goes down to the shot noise. But going to the high repetition rate brings two challenges. So the very first challenge is that at this peak intensity and average power, how the soft tissue is going to react. Are we going to damage it? So the whole time we are motivating the approach for in vivo super resolution microscopy. So how is it going to react to a high repetition rate laser pulses? And the other thing is that if we use this kind of lasers, then generation of these short pulses is going to be very challenging. So I'm going to address these challenges one by one. To understand how the soft tissue will interact with our short pulses, we did a study, I would say very complete study in this matter, that we studied the interaction of these laser pulses at different frequencies and repetition rate with a live zebrafish. So why zebrafish? Zebrafish is a very well-studied animal model, and they also have a capacity to regenerate their spinal cord. So it is that gives us some parameters to look at, right? So what we did, we just shined these laser pulses to the spinal cord of the zebrafish and try to see at which parameter we are going to damage it or cut it. Then how we defined or observed damage. So we had the neurons and glial cells, of course, labeled, right? Then you can see afterwards that if they are cut or not. And we also had the skin labeled to see what is the depth of the damage and when it's happening. And we also looked at some regeneration dynamics. So when the regeneration of the spinal cord happens, you have some proteins like macrophage and fibroblasts, which are going to the injured area and start to regenerate the process and heal the injured part. So if they are present, it means that there was a damage. If they are not present, it means that everything was at least at our sensitivity fine. So if I sum up this measurement, so we repeated this measurement for about 100 fish at different scenarios. And then here you can see how the damage probability changes when moving from the UV light to 550 nanometer and 1030 nanometer, and how it also scales with the repetition rate. So it is we could obviously see that if we are shining laser pulses at 1030 nanometer, the peak intensity damage threshold is much higher. And also the gap between the two repetition rate closes. So if I just translate this curve to its mean values, then you see how it scales at these three different colors. And also it shows that at 1030 nanometer, the process is very nonlinear. So if we had a high repetition rate pulses at megahertz, then the damage threshold was not very different from 127 kilohertz repetition rate laser pulses. So that most of the damage was happening because of the peak intensity, not because of the thermal issues. So, right, we also observed that if you are shining 1030 nanometer laser pulses to the zebrafish below this damage threshold, you can increase this irradiation time for our scales infinitely without damaging the sample. But this wasn't the case for shorter wavelengths. So then this study showed us that the wavelengths that we chose for this microscope is in a safe region. Our peak intensities are fine. And the amount of heat and repetition rate and power that we put on the sample should be fine in future. That's where that's the region that then we chose for the excitation pulses of this microscope. Okay, so the other challenge is that if you want to use these high repetition rate lasers, most of the time they have microjoule level energy, so it's really hard to generate very short pulses from them. There are not so many techniques, and then of course you have thermal issues, right? Because you have a high power system. What the technique that we chose for generation of these pulses, we chose this single ring hollow core fiber, and we have them in two different regimes of operation to generate our pulses. So if you gas fill this kind of fibers, then based on the dispersion of the gas and the combination of the fiber, you can run them in two different regimes. So one is that you can have pure SPM, where you have spectral broadening based on cell-phase modulation. And the other regime is that if you engineer it and with the pressure, if you engineer the dispersion and the pressure of the gas, you can have it in the solitone self-compression regime. How does it work? This is your input pulses, and as it propagates along the fiber, you have a spectral broadening. And at the same time, in the time domain, over the fiber, your pulses get compressed. So it's like that you just get at the output of the fiber very short pulses. So we use these two regimes for generation of our pulses. For the laser, we had a carbide laser, a commercial one. You can buy it easily, very nice lasers. And then for the first stage, we send the output of this laser to a 50 centimeter argon field fiber. And then we have some chirp mirrors to correct for the dispersion. And if you look at the output, we generate then 7 femtosecond pulses with a very good efficiency, with a total efficiency of 82%. Then these short pulses are sent to the second stage of the fiber. It's the same fiber, but we just use a different gas at a different pressure to tune the dispersion. And here we have the solitone self-compression. At the output, we have like 3-4 chirp mirrors, and these chirp mirrors are there because we have a window, and that's for compensation of the dispersion of these windows. So if you look at the output of the second fiber stage, you see that we generate this octave spanning spectrum, and they are very nicely compressed after these 2-3 reflections to 4.5 femtosecond pulses, which is about 1.5 cycle at this wavelength range. The beautiful thing is that right at the output of the fiber, you have a sub-cycle pulse. It's just, we cannot, with the current technology of the chirp mirrors, we cannot control the dispersion better than this. So these pulses are used to generate our excitation pulses via down conversion, and also we use it as a probe. So how the excitation pulses are generated, we have these broadband pulses, and we use intra-pulse difference frequency generation in a piece of BIBO crystal. And then we use the pulses again in our field sampling setup to read the electric field. Now here you can see that this is the electric field of the excitation pulses that we read very nicely. And then if you Fourier transform this, you get the spectrum. And we have a very high detection sensitivity. Here you can see that if you reduce the amplitude of our field by 8 OD, we still can detect the electric field very nicely and resolve the spectrum. So just to show how this excitation and detection works very perfectly, this is a very typical measurement in the lab for a very low concentration of the water vapor molecule. And here you can see the excitation pulses, and there it's not visible even by eyes, the molecular response. If you just Fourier transform the gate, the trailing edge of the pulse, you can resolve these two absorption frequencies of water, which matches very well with the Hytron data. We are talking about very low concentration of water. And in the normal case, if you Fourier transform the whole thing or look at it with other spectroscopic technique, you see nothing. Right? So I just have this to show you how sensitivity is high. So then we calibrated the system, and we see that we can detect down to 4 femtojoule level. What does it mean? If I put everything in a curve and compare it with the current techniques, field detection techniques, which are in the market, so at these frequencies, we push the sensitivity down to here, to the femtojoule level. So then this is the work that we are going to submit when I go back, hopefully, that I can look at the manuscript once more. So we calibrated it, and we checked many other kind of alcohols and liquid. Then here, for example, you can see our measurement of this ringing for the atmospheric water vapor. So this is the gas phase. The response is long, right? So we measure only for 30 picosecond, and you can see that we can resolve the resonances and the overtone very nicely. And if you go to the water in the liquid format, which has been very difficult to be measured at the overtone for spectroscopies, you see that the ringing dies out at around 1 picosecond, yeah, because you have water, the molecules, they just kick each other. And then we see that at very low concentration, we can still resolve it. And very nicely, we looked at the ethanol, and we showed that we can resolve the overtone excitation, overtone band of the ethanol, which has a very low concentration very nicely. So these are just proof that we have a very extraordinary sensitivity in our device. So, but I was talking to you about the microscope. This is what we are doing on the microscope front end. So now the setup is almost ready. And then we send the excitation pulses and the probe pulses to the microscope geometry. For the focusing, we cannot use standard objectives, right? Because the pulses are very short. If we go to one of these lenses, the pulses are going to be, I don't know, hundreds of femtosecond long. So we are using a reflective objective. And then it's kind of, it's also a research on its own, right? Because the reflective objectives that you can find in the market, they have the NA of 0.5. And you want to have a high NA, right? So we are following two paths. One path is to just combine these reflective objectives with the Microscope lens, right? That it also led us to put immersion medium if we need afterwards. And the other path is to just we are developing our own microscope objective, reflective objective with a very high NA. You can go up to 1 if you do the design correctly. So the lights are at the moment focused to the detection crystal, and the sample is placed on the detection crystal. So the sample has to be on the nonlinear medium, right, to get this the response of the molecules before their diffraction. And then in the transmission, it's sent to our field detection technique. So how does it look like in the lab? It's not. I'm not talking about the giant system. So it's like half an optical table, and you can do it much smaller if you want to rebuild it. And this is where the pulses are generated and then go down to the microscope. But we need to prove that we have a sub-diffraction limit special resolution, super resolution. And to do that, we should have a target, right? We should have a target that we know that these objects, they have this distance from each other, and then we have to show that we can see them, right? Development of this microscope target was also a kind of project on its own. For this one, we are collaborating with a group of Ilka Kriegel at Italy. Their research is on these ITO nanoparticle films, right? That they happen to have absorption at our frequency, at our excitation field, pulse frequencies. So they, at the moment, they are making such a structure for us with the ITO and gaps that we can put our pulses on and we see up to which separation we can resolve these stripes from each other. We already tested the these kind of samples in our setup. We can see the absorption, and we can distinguish actually the different thicknesses of these samples down to the monolayer. So I'm just saying that the sensitivity, our sensitivity is so high that we can resolve the absorption of the ITO at the monolayer very nicely and distinguish it from the two-layer system. So this is a work in progress. So I very much hope that we get by end of the year our target and we can show it. We can send our laser pulses to it and show that we have a sub-diffraction resolution. Okay, so but you might want to say, okay, now you have this very nice microscope, but you have to scan your probe pulses over the excitation pulses, and that might be slow. Or you might want to say that, what about the fact that if I want to see things live, right? At the moment, our scanning is happening at, so we have a millisecond scan, right? We can read the whole electric field at the millisecond time scale, but you might say that we want it fast. So this is a project that we also worked on. The work is on archive. You can have a look at it in more details. And that was, again, based on the fact that when your ultra-short pulse interacts with molecules, the response of these molecules are sparse in the frequency domain. So you don't absorb at all the frequencies that they are present in your ultra-short pulse. So then you are in principle you are just oversampling a sparse response. And then we thought to just implement compressed sensing on resolving the electric field of light and see how well we can see for very sparse samples. Then this is what we've done on a terahertz setup that we have in the lab also for other experiments. And we combined the system with the dazzler. That why we had this acoustic scanning or dazzler, because then it lets us to move the probe randomly on the electric field of light and then capture the correlation signal. Why randomness? Because if you have a sparse, let's say, problem and you want to use compressed sensing, then you don't want to have correlation, right? So you want the measurement to be completely random. So this is what we successfully performed. So I just jumped to here. And we developed also two kinds of code that you can find online to just retrieve this data. And then you can see here that, for example, in this curve, very nicely, here it shows the frequencies that the absorption happened. And here it shows that how the response changes when we reduce the sampling points. And here you can see very nicely that we can resolve the molecular absorptions beyond the noise frequency. So very nicely, we can break this limit, and we are not limited anymore with the noise frequency, and the measurement is super fast. So this is the measure that we performed for accelerating, let's say, time domain or field resolve spectroscopy. Okay. So these tools that we, at the moment, the institute that I live in at the moment, there are quite some biologists around and they are very excited. So we are having a cell in the setup. We are looking at the cell cycle and calibrate our setup for biological application. But you can think about the fact that these tools with this sensitivity are also interesting for looking at other type of problems, right? And one problem or issue is the gas spectroscopy currently, especially the short-lived climate pollutant. So these 4 categories of pollutant, they have a big contribution in the climate change. They don't stay in the atmosphere for a long time, and it's very hard to measure them or to quantify them to be able to just take action against them. So what makes it very difficult to measure them is, of course, is water in the atmosphere. That's the green curve, right? It just absorbs everywhere. So you need a very sensitive tool with a bit of twist to be able to capture this kind of their fingerprint in the atmosphere. But so, for example, methane is the one which is very damaging. And if you look at the absorption spectrum of the methane, then you are going to see that there are some gaps of hopes, right? That the water doesn't have absorption, but methane has absorption set. So this is so it's like spectrally gated responses. So this is the spectral range that we aim for. And we developed a laser system, which we are going to combine with our detection technique for a very sensitive field result spectroscopy of the methane in the atmosphere. So what is our system? The system is, of course, based on ytterbium YAG thin disk lasers. So they are, the system that we have is a 25-watt laser operating at 15 megahertz. And we coupled it with the optical parametric oscillator, which operates at its second subharmonic. So at the moment, we are working at the second subharmonic, but in the long term, we are going to go to the higher subharmonics. What does it mean? This is a way to increase the repetition rate, right? And so kind of cheating. So that, let's say this is your cavity, you send a pump, you generate a signal, and after 2 round trips, again, your pump meets your OPO pulses in the cavity. So then your cavity is going to have a 30 megahertz repetition rate. So this is the system that we developed, and it works pretty nicely. We are still working on the locking of the system. And if you tune the cavity length, then you can, of course, excite different wavelengths, and you can have a tunable system. So we are at the moment working on the locking of the system and also controlling the dispersion inside the cavity to be coupled with our field detection technique. So I just don't know how much time I have left. Should I?
About 10 minutes.
10 minutes. So, okay, then I just very briefly mention also, because this is one of my favorite kind of project direction that we started recently. So I'm not going to show you so many results. It's like work in progress, but I just would love to show you the vision. So we started to work on sustainable solutions because I think all of us should contribute, right? There are so many issues that I think it needs the help of all the scientists to be solved in the world. And we got interested in the solar lasers. So when I was making this slide last week for another talk, one of the colleagues, I was putting the title Solar Lasers Why? And the colleague was passing by and he told me, why not, right? So that's why I turned it to why not, really why not, right? Besides many reasons that one should build a solar laser, we are very much interested in their application in this very specific direction, solar power, space-based solar power. So what is this one? This is a very old idea, I think, by a scientist in NASA, which is taking in 80s, right? Which is taking momentum these years. And I know that ESO, which is the space, the NASA of Europe, and JAXA are trying to realize it, right, in space. And what is the idea? The idea is that the solar cells that we have on the Earth, they are not very efficient, right? And efficiency is an issue that we are all concerned about these days, right? And it turns out, if you do the numbers, very surprisingly, okay, and then you have nights and days and clouds and atmosphere and all this kind of stuff. But it turned out that the scientists in 80s who did the numbers in NASA, it turned out that if you put the big lens, let's say, in space, and you focus the light, the sunlight, to a gain medium and convert it to microwave or laser, and then beam it to the planet Earth, and there, again, convert it back with a photovoltaic cell, it makes more sense. So you get more efficiency, although you have all these expenses, right, to put everything in space and operate it and so on. And then you gain more in production of the sustainable energy. So beside that, so that makes solar lasers very interesting. So at the moment, what ESO is doing, the NASA of Europe, is that they are having this system, they are designing this system and to convert the solar laser to microwave. Why? Because they can have 80% conversion efficiency. And they are planning to beam it to the planet Earth. What's the problem? The wavelength is large, right? So then you need a 10 square area to convert this back to electricity. And then if you think about the ecological effects that can happen on this 10 kilometers, you don't want to pass by that region probably also, right? So that's why lasers are good, right? Because if you put a laser, then you need a 1 kilometer square, 1 meter square area to convert it back to electricity. But then what's the problem with the laser, or why they are not done yet? I'm just showing you in the next slide. But before that, I just want to tell you that that these solar lasers are, of course, important for remote power beaming, right? For the areas that we don't have access with electricity, and also for the interplanet communication. So there is a lack of this kind of lasers also, that if you want to communicate between Mars and Moon, so the diode lasers are multimode and they don't have the quality that you would like. So you are looking for solid state type quality with this kind of lasers. So what is the problem with the solid state solar lasers? So if you look at the literature, this is the graph that one of my students made, and you can see the momentum, right? So they have been shown in the solar lasers based on Nd:YAG. They've been shown in the very early days of the laser, right? And then you see that the progress was very sparse because very soon people found out they can pump a laser with a laser, right? And it's much easier, more efficient. You don't have to deal with the spread K vector of the sunlight, right? You can tame it in the lab. But then around here, we all noticed that, okay, we have to find a solution for energy and we can't just go on like this. And people started to work on it. So what's the problem with the current solar lasers is that their efficiency is so low. So their efficiency is 1%, and that has to be turned to a two-digit number. Oh, did I pass by this? Oh, I don't know why I can't. Okay, so this is what. So we have a lab in the parking lot of our institute, where we have a very big Fresnel lens. I mean, for our standard, and then we developed a laser cavity, and of course concentrator to just focus of the Fresnel lens to a tighter spot. And we cool down the gain medium. The cooling is a story on its own, and we are trying to make it more efficient and so on. But I just give you a little bit of hints that what are the fronts that we are working on. So the first front is that we need novel type of concentrators. At the moment, there are these non-imaginary lenses to concentrate the light on the solar panels, and it's fine if you have a spot of 1 millimeter, right? But to get a laser running, you really need high intensity. And you need to be able to focus the sunlight even to a tighter spot. So it's fine if you lose phase information. So it can be non-imaginary lenses, but you need to make it tighter. So this is a kind of thing that we started to do inverse design, and it's a work in progress we are developing. And the second issue is that the cooling strategy, especially if you would like to put something in space, you don't want to have a big bucket of water which cools down your system. And very preferably, you would love to have a kind of optical cooling, right? That you get rid of the heat via radiation. So this is also a concept that we are working on it, some theoretical work at the moment and design system. And of course, we need all to work on new gain medium, which are adjusted to this kind of problems and applications to be able to get higher efficiencies. Okay, so with this, I would like to end my talk. So I mainly talk to you about these new techniques that we developed in my lab, which we dubbed femtosecond fieldoscopy. And it's based on using ultra-short pulses for sensitive super-resolution label-free in vivo microscopy. What we are interested in, and we are setting up in the lab at the moment, we are interested in detecting the neurotransmitters, which are the molecules that they are carrying a message from one neuron to the other with our microscope, because they are very small, their signal is very faint, they are not visible. And we hope to be able to visualize them in the coming year. And of course, I was sitting in my office, I would say like 80% of the time, and the work is done by a team, very vibrant, very young and creative. The main two PhD students, Anchit and Andreas, worked on the development of the system. Soyun did the measurement on the fish. Kilian is setting up the Raman. Ani is active in doing the gas spectroscopy. And I have Michael, who is very, very creative, and he pushed the front of the solar lasers. Yeah, thank you very much.
Thank you very much. We have time for some questions. Yes.
Two quick questions. In the microscope, how thick is the nonlinear crystal that's under the biological samples?
So the nonlinear crystal is 50 micrometer, and you just adjust the thickness with the bandwidth of the excitation for the phase matching, right? To get the some frequency generation with the whole bandwidth running.
Yeah. And then the second question was when you were talking about the solar laser, the cooling of the gain medium optically, are you going to use the anti-Stokes fluorescence for that? Okay, cool.
It's not that easy, right? Because if you think about it, the sun has all the possible frequencies, right? And then, so I'm telling you a bit more because it's my favorite thing.
Center wavelength of the solar laser?
Yeah, that's actually, it depends on your gain medium, right?
Just wondering if it was eye-safe.
Oh, I say, right. So I think if you want to beam it down, then you look for something that goes through the atmosphere very well, around 1 micron. But for the cooling, so what you would like to have here, at the moment we have Nd:YAG. Why Nd:YAG? Because it's a 4-level system. And if you have a 4-level system, the threshold is low. So if you can't focus the light too tight, very tight, still it's gonna lace, right? Why we are doing these things? Because we want to focus the light tighter. Why tighter? Because if you can concentrate the light tighter, you can put ytterbium YAG, not because it's the thin disk and I loved it, but because if you do ytterbium YAG, then you have the chance to do anti-Stokes cooling, right? So the gain and everything matches very well. But then it's a 3-level system, the threshold is higher, so you have to concentrate it even, you have to concentrate the pump even tighter.
Okay, thanks.
So for the Femtosecond, so what's the temporal resolution and how do you achieve the delay between your probe and pump?
Yeah, can you repeat the question?
So the question is that for the fieldoscopy measurement, what's the temporal resolution and how do we scan the delay fast? So let me just take you to this. So the temporal resolution of what you measure is defined by your probe pulse. So the shorter the probe pulse, then you sample better the electric field. And what is the rule of thumb? You want the probe pulses to be shorter than half cycle of your excitation pulse, right? Because it's above that cycle, then you are going to undersample. So at the moment, the delay is on the probe is on a delay stage, which is a kind of, I forgot exactly the name, but it's so it's like 2 meters and it moves quite really fast, right? Yeah.
I just think it cannot provide you such a fine step. So
okay, so then yeah, there is a catch there. So then you are right, because then it doesn't read the positions very nicely, right? But we don't read the positions via the stage, but we have an interferometer. So we have a CW light going through the whole system. And we are reading the fringes, right? And from the fringes, then we read out the...
So that's why you don't need to you just need a millisecond to get the.
Right, right. So, and then you have to do it, otherwise this is like in air. And then look, this guy is like 15 femtosecond. And if you want to sample all the points, the jitter is there, right?
See, it's
Yeah.
super hard.
Yeah. But if you read it optically with fringes, then you exclude the jitter from your scale, from your measurement, and then you can resolve. We had no chance by the delay stage, right? You can never measure it.
Okay, thank you.
Oh, yes.
So on your slide about linear field results spectroscopy, you mentioned you were able to sense very little amount of water.
Nanoliter. So,
So I was wondering, how did you set up that sample, and can I extend it to, for example, more complex systems like cells?
oh yeah,
you have
that's
water.
that's what we are gonna do. So if you want to know the number, let me find this slide. So we are down to, to 1 digit nanoliter. And so this was a tough measurement. We had to do it simple because we developed something new. And the first thing that we need is that to show people that they can trust us. So how they can trust us is to show them that the things that they also saw with their device, we can see with that precision, but with higher sensitivity. That's why we did it on this, because there's also literature around this kind of liquids, right? So then people can compare and say, these people can see nanoliter. We didn't see overtone, they can see. So how these samples are done, we have a sample holder, which was, we had to engineer it at home because it's in principle to glass, and then, we made it with these 3D printers at home that you can put very tiny spacers, right? And then we inject the liquid in between and so on. So if you want, you can contact me. I'll send you the design of the sample holder. But if we put cells, at the moment we are putting cells. I don't have the results, but we have the field measurement of the whole cell response measurements. So these are ongoing measurements. I didn't include them because we are still doing data analysis. And what we look at as another proof of principle to attract the biologists is that we are doing the measurement to show that we can detect the cell cycle, right? That it starts, divides, right? That we can chemically read the whole response of the cell cycle. So this is an ongoing measurement.
Okay.
So you know that when you come up with a new word, there are always people who say, do we really need that new word? Right? And so fieldoscopy, is that just spectroscopy?
So fieldoscopy, so you can say that there is a field result spectroscopy, which is, right? At the terahertz wavelengths, people read the electric field of light.
That's
right?
what I was going to ask.
Yeah, exactly. No, you are absolutely right. Yeah. So the whole thing is that no one could read it in ambient air yet at the petahertz frequencies. So we refer to the fieldoscopy to our microscope because we get sub diffraction limit, or we are going to show it very soon, sub diffraction limit images, which are field results, right? So this combination hasn't been around.
Yeah, so I think, but isn't that really that, yes, so you say yes, terahertz, the spectroscopy is fieldoscopy in the terahertz domain, right?
But not microscopy. It is not microscopy. I think that's the.
You want to push that in the microscope and also to much shorter wavelengths in the terahertz, the two things, right?
To the microscope and to the petahertz. So
Higher frequencies.
Yeah.
Okay.
So I think I should have it somewhere at the back of slides, because we did so that's why we are in. I think I have it on another slide. So that's why we are interested in Raman. So I have a curve that it shows where the diffraction limit of the Raman and CARS microscope, because with the near infrared and mid infrared, of course, the diffraction limit is huge, right? So if you do CARS, then you can go to, there are many of them, right? That people could show that they can go down to 400 nanometer, but at high intensities, damage and stuff, but there is no sub 400 nanometer label free. And then with this setup, then we show that we can go below 300.
So CARS, is that fieldoscopy?
CARS, no. So CARS is just that you have, CARS spectroscopy, microscopy. So with the CARS, you measure the intensity of the light, right? So these are now with the field measurement, you have access to the electric field full electric field. So you have intensity and phase information. So if you want, these are like future plans. So if you would like to combine it with phase imaging and getting spectroscopic information at the same time, right? Or tomography and, OCT, we want to combine it with the OCT, right? Because then you have chemical information and OCT at the same time.
Thank you very much. Okay.
You can continue that at the
Yeah.
breakfast meeting.
What's in a word? I mean, seriously.
All right, we should probably have time for one more before we have to make room for the next class. Anybody else, any questions from folks online? All right, well, if not, let's thank Hanieh.